All right, good morning everybody. Today is a bit long lecture. Good morning everybody. Today is a bit long.
So YouTube close.
So sorry. I'll try to cover some area of CFD people are using for respiratory flow modeling, and also a little bit of cilia movement, and also the molecular dynamic simulation. That very, very briefly, but mostly the computational fluid dynamics. So, just guess how large is the surface area of an adult lung? Do you have any idea how large it is? And also guess how long is the aggregate length of our airways? Do you have any idea? Because we have very tiny lung here, but the surface area, how much? The surface area is like a tennis court. Okay? If you just combine all the surface area of a lung, it will be like a tennis court. Okay? And the length, if you connect all the airways, the length will be from Melbourne to Perth. So it is about 4,000 to 5,000 kilometers. Okay? So it's huge. So before we start this lung modeling things, I just need to give you some lung anatomy, because this is the term sometimes I use. So if you don't know where it is, so it will be hard for you to understand. All right, you see the left image. So there are two ways we normally inhale the air, through nose and through mouth. Okay, and also when we take the medicine, we also use both. Okay, like the inhaler we use mouth, but there are some other things. There are some other. I know that for COVID, they also spray something through the nose. Okay, so there are some medicine we can use like both in nose and through mouth. Okay, but we found that nasal drug delivery is more efficient than the through the throat. But it's a very complicated airways through nose, and it has couple of names. You see from the nose, and then we have nasopharynx here. They call it nasopharynx. It's on top of your just tongue here. Okay, and then oropharynx. Oropharynx is here, just your vocal cord, just up there, and then we have hypopharynx, and then we have larynx. So larynx is a very, very complicated area. It actually connect your upper airways with your trachea. Okay, it is very, very tiny there, very, very small, tiny. That's the reason. Even though your Reynolds number is very, very small, even 100, still you can experience a turbulent flow, because very tiny there. So the local Reynolds number is very high, because the velocity actually accelerates there. And then we have a long trachea. This is the trachea, long trachea, and then it separates this and that. And then we have how many lobes of a lung? Do you know how many lobes of a lung? Anybody? So 5. There are 5 lobes. And do you understand why you have, it is not symmetric, why you have 2 one side and 3 other sides? Yes, because we have heart, so heart actually occupies some space. That's why we have 2 on the left and 3 on the right. Thank you. So, and from here we just specify how we understand that. We just specify this one we call like a generation 1 or generation 0. Some researchers they call it generation 1. Okay, then it bifurcates into 2. So this area they call it like a 1. and after that 2. So this way we have 23 generation. Okay? So 23 bifurcation or 23 generation. So that means, so how many outlets then we have? How many outlets? We have one inlet. So how many outlet? Anybody? 2 to the power 23. Okay? So we have huge number of outlets. So that's why when you do the modeling is very hard. You have to specify all those outlets. So you need a very big screen and get all the outlets to specify the outlet boundary condition. So in that way, we have until generation 18, we can easily identify. But after 18, we cannot identify. They are actually covered by acinus. Okay? Acinus means the alveoli actually start from there. So we have here like a balloon-like structure. Okay? Here you can see. And then this one is actually the alveoli sacs. So you know what the alveoli does is just exchange the oxygen and the carbon dioxide. Okay? And Professor Chakraborty already explained about the capillary or blood flow. The capillary means the smallest the channel through the blood actually passes, the very, very smallest. So near the alveoli, this is actually the smallest capillary. Okay? Smallest capillary is near the alveoli, on top of the alveoli. There is a reason for that. Do you know why? Because that capillary is very tiny, and the red blood cell, the diameter of the red blood cell is about 6 to 8 micrometer. But the radius of the capillary may be 3 to 4 micrometer. So that means when the red blood cell goes through that, it actually squeeze a lot. Squeeze and its membrane expand. So once its membrane expand, it actually exchange the, due to diffusion, exchange the oxygen, okay, and carbon dioxide. Take the oxygen and release the carbon dioxide. So the red blood cell collect all the carbon dioxide from our cells. Our body is always working, so they collect those wastage things like carbon dioxide and some other wastage material from our body and bring them to the heart, and heart actually pump to the lung, and lung then purify. Take the carbon dioxide and give the oxygen, then it come back to the heart again and then pump the red blood. But when it comes to the lung, the color is like a bluish color, because no hemoglobin that time. So that's why those capillary is very, very tiny. So we'll discuss this one later on, and this is some CT scan based geometry, and I'll discuss about how we do it. So now, why do we need to study the lung? Because it is especially for the modeling. So yesterday Professor Chakraborty told that not always possible to do experiment or some other study, because you cannot take your heart out and lung out and do the experiment. And also through the numerical simulations or computational fluid dynamics simulation, you can analyze a lot compared to the experiment. Experiment you just get very, very limited results. But numerically you can do whatever you like to do. You can probe any points and then you can analyze the results, but in the real life, real experiment is not possible. So you see here the air quality in Delhi. So you know what is the air quality now in Delhi? This is the winter season. Okay? So you see here, and we are inhaling lot of these dust particles. Okay? So you know the stubble burning, right? You have a stubble burning near Punjab. So they burn the rice, okay, the paddy things, and then it actually produces a lot of unhealthy smoke, and it comes to the Delhi, I guess, and that's the reason it's so polluted. So if we inhale this one, how it actually affect our lung? So that's what we need to study. And not only that, we have some other pollution. That pollution is like car exhaust pipe produce a lot of ultrafine particles. So there are a couple of sizes we need to consider. It's called PM 2.5, PM 10, and more than that. So PM 10 means the particle size less or equal to 10 micrometer. Okay? And PM 2.5, it means the particle size is less or equal to 2.5 micron. Those are very dangerous because it goes very deep airways. Okay? When you inhale the ultrafine particles, it goes very deep airways. But PM10 is also dangerous. Recently we found that it's also dangerous, but more than 10 micron, it normally stuck. At first it is stuck in our nose here. See, we have a lot of hair inside the nose. It has a purpose. Sometimes we see why we have hair in the nose, but it has a purpose. So that actually stop, okay, all the particles you are inhaling. That's the first barrier. And then the second barrier is our mucus layer. Okay? So our all conducting airways has a mucus, very sticky mucus. So mucus, any particles actually go on the mucus, it's actually deposit. And then through the mucociliary clearance, we are actually eating every day. I mean, every 10 seconds or 15 seconds you are eating, right? You feel some itchy after 10 to 15 minutes and you are eating. So that means all the mucus is coming up. It's a one-way movement. One way coming and feeling something itchy here, and then you can just eat. So this is the way mucociliary clearance is happening. So a lot of barrier before it actually attack our lung. But if it is like very highly toxic particles, so there are some problem. It can penetrate into the epithelial tissue. And then the other thing is air quality in Dhaka. So Dhaka also the similar as in Delhi. So they are champion for a couple of years. I found that they are on the second most polluted country, capital city, and there are a lot of things happening. So that's why we really need to understand what actually is doing it. The another recently thing is that I'll show you later on. That's called the micro and nanoplastic particles. Not many people know yet because we are everyday life. We are using plastic bottle, we are using plastic bag. So those things are actually affecting severely to some marine life. Okay? So not only that, we realized recently that it is also in the air. You know why? We are using the water bottle and throwing it outside, and it is exposing the sunlight, and with time it's becoming very hard, and then when you like is interacting with something and becoming small and tiny, like a micron or nano sized particles, and then it is actually on the air and we are inhaling it. So recently we found that in our body, almost every organ we have it, like in kidney, in respiratory system, in blood, even in mom's breast milk, we got this tiny microparticle. So now it is also very dangerous, but we don't know yet what is the consequence of having that. Okay, so we found that maybe it makes some lung cancer or something, but still there is not much medical evidence. So that's why still we cannot say that no, don't use plastic things. We cannot say very strongly. So that's why we need to do some research. So what is the source of PM 2.5? In 2015, these are the recorded. Only 59 good days of air quality in 2016. This is based on the Dhaka, okay, in the Dhaka city. Maybe very much similar to your Delhi. Only 59 good days. All other days are like full of polluted. Over 80% of urban residents are exposed to air quality levels that exceed the World Health Organization limit. So they have some air quality limit. I think it is 80 or something. And it is always more than like 200 or more than 200. It's very dangerous. And 20% reduction in exposure to urban air pollution would save 1,200 to 3,500 lives annually and avoid 80 to 200 million cases of illness. Okay. So in 2015 alone, Bangladesh had 122,400 numbers of death attributed to PM 2.5 You see how severe it is. And Dhaka ranked 44th in terms of PM 2.5 pollution and 71 in coarse dust pollution, PM 210 in 2015. So now, normally it's a typical day who are doing servicing or like doing some jobs, how they spend their time. So most of the time they spend like home, about 42.8%, okay, of their whole day, 24 hours, they spend at home. And then outside 8.23%, office 38.23%, and out and about 10.73%. So that is the average one people use. And we breathe between 4.5 to 42.5 liter of air per minute. It depends on your resting or your running or your sleeping. Okay. So that means we breathe in one day the total 22 crore PM 2.5 particles. You see how much it is? 22 crore, right? Yeah, 22 crore PM 2.5 particles we are inhaling in every day. So that means we are breathing about 220 million tiny PM 2.5 particles per day, just over 2,500 per second we are inhaling the ultrafine particles. And where are we breathing these particles? Home is about 23%. We are actually producing a lot of these particles at home, especially in the village, in the countryside. So people are using like wood burning. Wood burning, they are producing a smoke. That smoke is very hazardous. Last time I came in 2022, I came in Kharagpur, and that time my family, my brother's wife, came to Kolkata for the treatment, the lung treatment, and she had actually COPD. Okay, then the doctor said, "You should not have COPD." I said, "Why?" "Because he's a woman, he's not smoking." "So why?" I said, "No, she is cooking every day, 3 times a day, in the morning, lunch and dinner, and it actually producing a lot of smoke, and that can affect." So the doctor argued with me, and at the end she actually died in couple of months. Okay, so that's why not only smoking, that is called another kind of smoking, who are cooking in the kitchen in the countryside. So that smoke particles is also very dangerous. So now a little bit about the background. So initially it actually started before 2000, and I was very lucky that the guy who started working, Hoffman, in 1990 paper, is a very famous paper. Luckily I met him in QUT in Australia, and that guy actually started working on it, like the modeling, and his student Farkas. I am also collaborating with this guy. So they started with a very simplified geometry. Okay, it's not like a realistic geometry, just a bifurcated geometry, because it is very hard that time to get the lung image. Okay, and then slowly it actually developed, and sometimes they got like the mid hunter, that is a mouse lung. So they try to many ways to improve, because those results they published there, it is far from the reality. Okay, our realistic lung. So that's why we need a very good realistic lung to describe the real things happening in our lung. So that's why we just collected some CT scan image when we started in 2012. We just started collecting some CT scan image of our lung. Okay, and then we started doing some post processing. You can see at the end. So and but when you do the post processing, you see here the lung actually is covered by the parenchyma thing. So you have to clean it up to get the airways. But when you clean up, some part of the airway is actually damaged. So you have to reconstruct it. So it is not a very simple job. But yeah, so when you do it, you see after the first processing, we get on the left side, and a lot of rubbish is still there, and some airways already gone. So we have to do some manual fixing it. Okay, you see here. So those after the fixing the manual things, we just extend some cut of things here. You see, we extended the airways. Okay, and then these are the geometry we got at the end. Okay, so now still all the airways, the outlet is now closed. You can see the outlet is closed. Also there are some holes on the surface, so we have to fix as well, and that everything we have to do manually. Okay, and then we get the surface segmentation like this. And now you see on the top, that one is closed, the outlet is closed, then we cut up, okay, and apply the outlet boundary condition. So these are the final geometry. So this final geometry we got about 13 generation, because after that is very tiny and it's very hard to get, because a couple of micron size diameter, and it is not possible from CT scan. We can do it. We can do some manual adding. We can add some manual way, but that will not be some realistic things. I think the 13th generation is still all right, and we also got the nose and the mouth both. Okay, so but in Australia it is very hard to get the ethical clearance to get this data from the hospital. Yeah, it is possible, but it is a very long way to do. So that's why I contacted someone in India, and we got the lung CT scan from India, and the India one was from here, because when you do the CT scan, they cannot do the whole lung CT scan. So they have to do part by part, from here to there and from here to there too. So I got this one from here in India, and I got this one from China. Then I connect together. Okay, so here you can see it's connected. It's connected here. It's a larynx. You see how tiny here. So so this is the complete geometry. So then we apply the mesh. We did an extensive mesh dependent test, because we had to face a lot of issue with publishing paper, because as I said before, everybody's lungs are different. So we cannot compare my results with your results, because our lungs are different. So how can you compare it? So that's why we have to make sure that our numerical results is correct. So that's why we did a very extensive mesh dependent test. We use 3 different types of mesh. This is called the hexa mesh. Okay, and you know the control volume we already discussing for last 5 days. Okay, so these are the equations we solve, the continuity and the momentum equations, and then we have the turbulence K omega model we use, and then the energy equations. I use the energy equations for some application of our lung as well. So here we applied some realistic breathing pattern we got from the experiment from the hospital. So what is the profile of this breathing? Actually it was like some discrete data, the one that TA showed you last time, and then from there we draw the profile and we just get some mathematical equations, and then we wrote the UDF. But there is some other way that he showed you how to use the discrete data as a boundary condition. Okay, but you can also do this. So you can see I use 3 different boundary condition. One is called the 60 breaths per minute. So that means when you are running, okay, you breathe very fast. And then resting is 30 breaths per minute, and then 15 breaths per minute when you are sleeping. So 3 different breathing pattern we use. The maximum for the resting or sleeping, it takes about 4 minutes per breath when you are sleeping. Sorry, 4 seconds, not minute, 4 seconds. 4 seconds on breath. And you see very interesting that it is not a sine function, but before we saw a lot of papers, they published this breathing pattern as a sine function, but this is what we just got from the experiment, and you can also experiment by yourself. When you inhale very fast and then slow down, and after that you give a bit pause. Okay, when you breathe out, a bit pause and then you breathe in again. So there you see at the end we have some pause. And then so how our conducting airways is made of. So you can see the mucus layer on top, okay, and underneath we have some cilia. Cilia is like a brush like structure. So we are cleaning the floor, right? That's a brush. So we have a brush just underneath the mucus layer. The brush is actually cleaning up. So brush is working like this always, okay. So pushing up and going down and then pushing up. So this is the way, it is one way movement, okay. The cilia is going down but that way. So this is the way it is always happening, and then the cilia actually is floating on the water, and underneath the water we have the epithelial cell. So that you see how many barriers is getting. So but still if some of your particles are very toxic, you can easily penetrate into the mucus layer, and then through this cilia it can actually go to the epithelial cell. Okay, this is our schematic of how we did our numerical validated results. We use 4 mesh density design, okay, and then we use 3 mesh element design, and then we use 3 mesh boundary prism layer design. Okay, the boundary layer we showed you like a 6 layers, right? We showed 3 mesh boundary layer to see the result is changing or not. And then we use 4 pressure velocity coupling schemes. So we have a lot of schemes like simple leg, Pichot, a lot of things. So we just use 4 of them, and then we compare our results and perform the mesh independent test. And at the end we got the result. So if you really want to see, because this is the very extensive way we did, and we just published this one in a book chapters. It's very details. The paper is the book is not in the market yet. It will be very soon. So now you see the 3 mesh, the top, and then the mesh element we just give on the boundary layer, okay, how we define, okay, and then we did some mesh dependent test. Okay, so this is the way we calculated residual, and then we just did some for density 1 to 2, 2 to 3, and 3 to 4, and then we compare our results, okay, from there, and then we just got our validated model. And this is the other way, is just we locally validated our model as well, like the nasal, the oral, the larynx, and from generation 0 to 13, okay, and we just also calculate how many particles actually escape, go out from the lung, from the outlet, okay, and not deposited. So this is the way. So this is for 3.8 million, we still call it coarse mesh, okay, and medium mesh 5.1 million cells, and fine mesh is 7.8 million cells. So this is the way you also compare our results.
What is the y-axis here?
Y-axis is the deposition fraction. Okay. So now these are some comparison with some previously experimental data. Okay. So as I said, it is not very quantitative. Result is quantitative, but you cannot directly tell that why it is not the same result as that, because of this every lungs are different. So that's why I said if it's close to that value, still accepted. So these are different lobes, okay, and these 2 experiment data, and this my previous PhD student, his result is that, and our current result. So for different tetrahedral mesh hexa mesh and the polyhedral mesh. So, these 3 type of mesh we got, result is almost similar. Okay. Again, as I told couple of you that there are some other way we do some validation, that is like for a specific part of a lung, it is in the trachea. Okay. You see for the trachea here, we just some other researcher, they calculated the deposition efficiency with the normalized particle inertial parameter, and then they have the results, and then we just also got our results, and then it actually follow the trends. So, in that way we see it is in the range, okay, in the upper limit and the lower limit. So, in that way we also validate our models. So, this is the maximum we can do validation for the lung. Now, at the end we just got this geometry, and these are the results we got. And then when we in 2012 we could not get up to the 13th generation because we did not have those software available that time. So, that time only we got only this part. Okay. And then we just use about 10 million unstructured tetrahedral cell, and we use the fine boundary inflation layer, hexahedral mesh we put on the surface, and then dense tetrahedral element at the bifurcation region. Okay. And then we did some mesh dependent test, and then we just study the 10 micron size particle deposition for 15 liter per minute flow rate, 30 liter per minute flow rate, and 60 liter per minute flow rate. And as you can see here that when the flow rate is very high, more particles are deposited because of the turbulent effect. Okay. Turbulent means it's going here and there, and then once it is it touches on the surface, it actually deposits. So, if you use use the Ansys fluent, there is a boundary condition called the trap boundary condition. So, trap means when the particles hit the wall, the particle will be disappeared, and then we record the coordinate on that point for the post processing. Okay. Because this particle is not the real particle in Ansys, it is just point particles. Okay. So, that means we only record the coordinate points, and we take all the coordinates at the end and get the geometry, and we just see this deposition. Okay. It is not like a particle is moving and going this way, this is actually deposited, is already in the a deposit in those area. So, from these results what we found that when the flow rate is very high, that means when you are running and we are breathing this dust particle and these things, it actually deposit on our upper airways a lot. And not only that, there is other hot spot, we call it hot spot, is this area, this bifurcated area. So, in biology they call it carinal angle. So, in that carinal angle here particle actually deposit. And another thing is when it actually clear, the mucociliary clearance time here is very, very slow. Okay. Because it is coming from this way and coming here, it is coming from this way and here, and then slowly moving from here to there. And you observe that if it is there for more than 7 hours, okay, the particle will be deposited inside the epithelial tissue if it is toxic. Okay. And this medium one is also you can see some more, but for slow breathing means laminar flow. When it is laminar flow, it actually follow the streamline of our air flow. Okay. So, if the flow follow the streamline, it actually goes along and it can go to the deeper airways. Now, here we see some quantitative results. All right. So, we just draw a line along the y axis, and then we see you can see from where those particles, most particles are deposited in for 3 different cases. I should show this one together, then you can see. So, that one is actually from here to there. Okay. So we just counted along the y axis and then we showed it here. So in 3 different cases you see the position specific particle deposition. So he see here it is about negative 0.082 or something. So that means it is here somewhere. So most particle actually depositing here. That's why I can see here. Okay. And here we just did for 3 different particle size, 1 micron, 5 micron and the 10 micron size particles. So in that case it was bit hard to do like a polydisperse particle that time in 2012, but now we have the Ansys has very good like system that we can solve the polydispersed particle, and we call those is monodispersed particle. So monodispersed particle means the single size particles. We can only simulate a single size particles. So that's why we have to run 3 simulation, 1 micron, 5 micron and 10 micron. But now you can use like a polydisperse. So I'll show you the in the tutorial how you do that. So you have to give the maximum and the minimum diameter. For example, maybe the minimum is 1 micrometer, maximum 10 micrometer, and then you have to show how you want the distribution. Okay, it is a normal distribution. Then they will show the middle value, the maximum. Okay, maybe 5 micron has the more particles, or you can specify which one has the maximum numbers, maybe 8 or something. Then the curve will be like that. Okay, this way Fluent can automatically distribute the particles. Okay, and here you can see the deposition efficiency in the upper airways. You can see the 10 micron size particles actually deposit for 60 liter per minute, deposit more, okay, compared to the 5 and the 1 micron size particles. So that means we just confirm that the larger particle actually deposit in the upper airways and the smaller particles go to the deeper airways. That's why I said PM 2.5 is more dangerous because it goes deeper airways. So PM 2.5 is like 1 micron. So that means this actually is not depositing upper airways. It is going to the deeper airways. So now this geometry I just got from America from one of our collaborators, and this looks like we call that time is a very realistic geometry, but it is not actually very realistic. What we did is we had some profile, like yesterday Professor Chakraborty showed you that how we get one dimensional path, okay, using some software is called SIM something, right? Yesterday he showed it. Yeah. So yeah, that one. So so we actually had this kind of path, okay, from the medical imaging. We got this kind of path. So based on the path, they actually designed this airways, because already we have the Weibull geometry. We know that the dimension of each like bifurcation or branch. We know the dimension. So if we know the path and if we know the dimension, it's easy to create it. So that's the way we just created this geometry. So until 2015, this geometry was very, very popular. All right. So then we use first and the best available 17th generation anatomical model with entire bifurcation branches. And here we just have 1453 bronchi up to the 17th generation. So that means if it is 17th generation, so the outlet or the bronchi will be about 2 to the power 17, right? But that should be very more than 1453, isn't it? Then why you have less? Because it is not possible to get all the path. So there may be some of these are only 15, some of these may be 13, okay? But up to 17 we have only 1453 bronchi, okay? The last one. So, and 34 million unstructured dead cells we just got. That is the maximum mesh we use in our HPC. So, our HPC cannot tackle more than that. We can use for PhD student, they can use maximum 64 CPU. They cannot do more than that, but if somebody does some very extensive research, they have more, or they can use the Amazon Web Service. So, they have millions of nodes they can use. Okay. And here we did some pressure and the velocity contours. So, you can see how this pressure is distributed. So, pressure is also very important here because there is a lot of pressure drop. Okay. When it come here, start from here, see the pressure drop, how much the pressure is dropping. Okay. So, for the drug delivery, so we need to understand this pressure drop. And then we just draw this line along this for 5 different lobes, and then we just calculated the pressure drop. So, these are the pressure drop. You see how this pressure is dropping from about 4.48 or something from there to the 0 is by in some cases for 10 generation is the pressure is 0 already. So, that means there is no pressure after that. And now here we just use some microparticle deposition during the fast breathing, when you are breathing very fast like 60 liter per minute. So, 1 micron size particle and 10 micron size particle. Okay. So, 10 micron size particle you see it is depositing in the mostly in the bifurcation region and upper airways, and for 1 micron size particles is coming to the deeper airways. So, again we just got from the close to realistic geometry that particle are depositing in the smaller particle is going to the deeper airways. And here we use 1 nanometer particles and 10 nanometer particle size. So, it is a different story because this they follow the Brownian motion. Okay. So, when the particle is very tiny like a nano size particles, they do not follow the particles for like more than 1 micron size particles. Okay. They follow differently because they actually like Brownian motion. Brownian motion means it's like going here and there. Okay. Yeah, it's dispersed here and there. So, that is why it is like work a different way. You can see it work as a different way. So, the 10 micron size particle goes to the deeper airways, but the smaller particle is actually deposited on the upper airways because of the dispersion effect. In Bengali, we normally call it like the rice pup or muri or khoi. Okay. When you just do using the how they call it like sand, this goes here and there, right? It's similar to that. It's actually happened there. And then we started. So, this is our first study for polydispersed particles, and we published in that scientific report journal, and it is from 1 micron size particle to the 10 micron size particle, and we can easily just find out here the 10 means the red one. You can see the red particles is almost the upper airways, and 1 micron the small one is actually going to the deeper airways. Okay, you can see clearly from there. And then we calculated the deposition efficiency, okay, based on the particle diameter, and we found that up to 10 micrometer, from 1 micrometer to 10 micrometer, we just calculated from the right, left and the total, and we just got some this equation. So, the equation is very accurate. It is close to r square is equal to 1. So, that means this result actually suggests that if you use more than 10 micron, so we do not need to do the simulation, we can directly use this equation to just calculate it, the deposition efficiency. Okay. So, now the one I just told you, how this microplastic and the nanoplastic particles accumulate in human airways, posing health risk. Okay. So, this is my very recent study, and we did a lot of review papers, and we try to understand what is happening all over the world with this. We published a couple of papers, and after that we did some modeling on this micro and the nano plastic particles. Okay. So, you see in the in Nature in this year they published, and they said that 16,000 plastic chemicals compounds found in the plastic, 16,000 plastic chemical. Okay. So, this chemical and more than 4,000 plastic chemicals are hazardous. Okay. So, I do not know because the plastic company, they produce those things and nobody cared that time what is in there. So, and they just found that there are 44,000 plastic chemicals are very hazardous for our health. And nowadays we are so much dependent on this plastic, we cannot stop using it. Okay. We can see when we buy some vegetables from the market, we just found they just put like this way in the market with the plastic cover. And we just found that the plastic wrappers are known to release some chemicals into the food. Okay. So, you now understand how dangerous it is. So, in the microplastic and nanoplastic are pervasive environmental contaminants that have been detected in human and avian respiratory systems very recently, not long time ago, very recently. So, these particles actually originate from both primary sources like the cosmetics and secondary sources like plastic degradation. So, what is cosmetic? How they are getting from a cosmetic? So, that means the women are spreading it, right? It's not only women, but you see there are some like some face wash. You know, some people I think they use face wash. In the face wash there are some small tiny particles. Okay. So, if there are some particles, then if you do the cleaning your face, it cleans faster and clean nicely. So, those small particles is actually the plastic particles, and when you are cleaning it, this particle is going through the water and going everywhere. So, and it is going to the maybe ocean or somewhere, and then the fish eating, okay, and it is going into the fish because it is not nobody can digest it, and then you are eating the fish, and so you are eating again. So, it is like a cyclic order, it is just is coming back to you. Okay. So, the health impact, so the nano and micron plastics are associated with various lung disorders, okay, including the COPD, okay, the fibrosis, asthma. Okay, so, this kind of disease, and the inhalation of these particles poses significant health risk due to their interaction with biological tissues, potentially disrupting endogenous surfactant and these cytoskeleton arrangements. You can see the baby is born and plastic particle everywhere. And now we can see the hidden things is everywhere in the air. And actually the more dangerous thing is like recently in Australia and some other developed countries, they already introduced the fully electric vehicle. India also trying to do it, but they do not have any lot of charging station yet. They started building it. Already Australia, they declared by 2030 there will be no like a fuel engine like the car engine. They will be replaced by the electric, fully electric vehicle by that time. Okay. But it is good for environment, it is good, but at the same time the battery size is very big and very heavy. Okay. So, and because of that, so the wheel in the tire is very, very big. I saw the Tesla car. So, the Tesla car battery like the wheel is very, very big, okay, because to carry the heavy battery inside. So, that because it is heavy and it is actually making some friction with the surface of the road. So, it is producing lot of like a microplastic and nanoplastic. You see, this is another pollution. Okay. Previously, it was fossil fuel pollution, now it is becoming plastic particle pollution. So, we need to think about it. So, the aim of this study was to utilize the computational fluid and particle dynamics to model the transport and deposition behavior of nano and micron plastic particles across the entire human respiratory tract, from the nasal cavity to the 13 things. Okay. And the methodology we use the CT scan based technique to get the geometry, and then we use some different breathing pattern, the slow, the normal and the fast breathing, and we also study the shape of the particles. So, we did different shape of the particles, because this plastic is very strong and it is not like always spherical particles. Okay. So, we use like spherical, cylindrical and tetrahedral shapes of particles, and we expect from this study to enhance understanding of nano and micron plastic particles related to air pollution impacts on health, and to inform the clinical and public health strategies and guide the regulatory policies. Okay. So, you can see here we just inhale those plastic particles, and this is called a spherical nanoplastic particles. Diameter is 1 to 100 nanometer size particles, and the right one is the same spherical particles with a diameter size of 1 to 100 micrometer. Okay. So, you can see the nano size particles actually going to the deeper airways, and once this is finished, then it will start. And on the left side you can see how those particles are actually deposited. So, a lot of particles actually deposited on the nose and that upper airways, because of the complex airways into the nose. Okay. So, particle deposit there, and on the left side we have the deeper area of the particle is depositing until the 13th generation, and here you can see from the trachea. So, most particle actually goes here. So, after we published this paper, we got a lot of media attention, because for the public health this study is very useful. So, all over the world, especially in India as well. So, a lot of newspaper in India they published our study, and also in Europe in so many different languages they actually told that this study, they said, I just read their news, they said that some comments, they said that we are keep telling that this is dangerous for our health, but nobody cares. Now see the study. So, what is happening? So, and we got a lot of the interview through the print and also the radio interview, and they just encourage us to do some further study. So, we are actually still working on this area. But as you know that we have a lot of limitation for CFD study. We cannot do anything else other than where it is depositing. Okay. So, we very quantitatively tell that this amount of particle depositing here. After it deposit, CFD cannot tell anything else. Okay. So, to do that you need to do some other study. If you still want to do the modeling, then the molecular dynamics simulation is important. You can do the molecular dynamics simulation, where you can see how this particle molecule is interacting with our lung surfactant, the lipid, the protein, or other surfactant materials, how they are interacting. So, because of that, one of my students is working in this molecular dynamic simulation for these plastic particles. And I took another PhD student, he is working on the mouse. He is working for the like a real experiment. So, he is using syringe, he is injecting the plastic particle through the nose of the mouse, and he wants to observe those where those particles are depositing and where actually it is going. Okay. So, he will measure not only the lung, but also the blood and some other cells in our body to observe where they are going. Now, this is another study. This is very interesting because last year I just got a news that the American President Joe Biden is using CPAP because he does a lot of snoring at night time when he sleeps. Okay. So, I don't know whether you snore or not, but some people snore at night, like make a lot of noise, especially if someone make this noise, I cannot sleep. I have some issue with that. And a lot of things happen, especially if the husband does it. So, a lot of actually separation happen, divorce happen because of this. Yeah, there are some record of that. So, to get help from this, so these are the machine can help you. Okay. So, this is called for the sleep apnea. So, it is also for health risk as well, because during the day we are conscious and we can keep our like our lung open, but when you get sleep, so the muscle of our lung become relaxed and actually is closed almost. So, when I breathe, it makes some vibration and this makes noise in this vocal cord. So, that is why if we can use any technique that can open up. So, that is why this CPAP machine actually developed. But this machine has a lot of concern that because they use for CPAP, they use like continuous positive airway pressure, CPAP, continuous positive airway pressure. So, that means they continuously pressurize the air into your through the nose or through the mouth. Okay. They use this mask. So, that use only nose. Okay. Because there are some people only breathe through nose when they are sleeping. Somebody use both or somebody use only mouth. It depends on the person. So, and then they give positive pressure. So, when they give positive pressure, you are sleeping, so your airways become large. So, there is no snoring and you can have a good sleep. So, but sometimes people don't understand that whether they have this sleep apnea or not. But there are some symptoms. So, if you feel like very dizziness during the day and very sleepy during the day, very tired during the day, I think you should see a doctor, sleep apnea specialist. Okay? And I can assure you that if you use this on, you will have a very good sleep at night time, and the following day you will be very strong, in every respect. So, you should test if anybody has this issue who does a lot of snoring at night time. So, so it is nothing but there is a machine that only pump the positive, continuous positive airway pressure. That is it. It is very, very simple. But our aim was like, because they are giving some positive pressure, the positive pressure can have some surface, they are damaging the lung surface or not. Because the shear stress, they create a lot of shear stress on the lung surface. So, we need to understand whether it is happening or not. So, that is why we actually did some testing, and we want to model, we want to change something if it is needed. And we found that the current system is okay. So, that is why the company, the ResMed is the biggest company all over the world, the US based company. So, now they actually they got support from our research. Now, they put our results in their website. You see, this is the proof our system is working perfectly. So, what we have done here is we just apply some positive pressure. So, that positive pressure is like you are irrespective of what you are inhaling or exhaling, is always giving you positive pressure. So, that means when you inhale is good, you are getting support, but when you are exhaling, you are not getting support, because you are getting like some obstruction, because you are also getting pressure. So, but because you are exhaling is automatically you are exhaling. So, who has not much like sleep apnea problem is good for them, but who has severe problem, I think CPAP is not good for them. They have some other things. We also did that study as well. So, you can see here the static pressure on airway wall for like without CPAP, the static pressure on the airway wall is lower. It's obvious. And then when you apply this, so is just higher, because we are applying more pressure. So, the airway will experience more pressure. Okay. The supporting force on airway wall for without CPAP is lower, but with CPAP is higher. And the airway wall shear stress and airflow velocity field we found is no effect. Okay. So, these are some study we did with CPAP and without CPAP. So, the pattern you see is almost the same, except some value. As it is too small, you cannot see this number. So, you can see the number here. The number here is like without CPAP and with CPAP. So, this is higher. This is lower. Okay. So, the dynamic alteration in area weighted static pressure, the y-axis, okay, through a single respiratory cycle, just like one cycle, a third or fourth cycle, we just use it. And x-axis is the time in seconds. So, A and B is the upper airways response. So, from that and that, okay, and A and B, and then C and D, the middle two, okay, across lung generations, and E and F is the entire respiratory system. Okay. So, it is too little, you cannot see it. Again, because we already validated our model. We already validated our model with lot of experimental results. We are using the same model, okay, applying some different boundary condition, but we are using the same model. So, that is why we said this model is already validated. So, we do not need to further validate this model, but you can do that. I already talked to them, the ResMed. One Indian researcher is working, and I have very good collaboration with him, and he said that he will give me some patient specific data. So, in future I will do some validation. Now, this is called the BiPAP. So, BiPAP means bilevel positive airway pressure. So, this is more advanced. Okay. So, CPAP and the BiPAP. So, BiPAP is like they give more pressure when you are inhaling and less pressure, but still positive pressure, less pressure when you are exhaling. Okay, that for the like very severe person who has like a COPD or who has a very high asthma or this kind of things, they can use this system. So, that actually helps them, and it has actually both. So, for CPAP, the range of the pressure is about 4 to 20 centimeter water. This is the unit. I do not know how to convert it from the Pascal, but that is called the 4 to 20 centimeter H2O. So, that is the pressure. But for BiPAP, they can handle like 4 to 30. So, that means if they need more pressure, they can use it. But it is strongly recommended, and you cannot actually do the change by yourself. So, you have to go to the doctor, and doctor can set it up. Okay, what pressure you need. You cannot do it by yourself. It is very like dangerous. Okay, if you set up by yourself, it is very dangerous. Every time you need, if it does not work, you need to go to the doctor, and doctor can do some assessment and can set up the pressure for you.
So basically, it is dependent on the respiratory strength or something.
Yes, and your health condition and how much you need. Then they will do maybe couple of nights, the whole night they will assess, okay, and then they will find the optimum pressure for you.
What volume we are actually inhaling and what pressure pressure it is required.
Yes, yes, that's the way they will do the assessment. Yeah, and this is actually very expensive as well. So the left one is about 700 to 1500 US dollar, okay, and the BiPAP is about 1500 to 3000 US dollar. It's a bit expensive, the BiPAP. But if you can buy the BiPAP, that can actually works both. And those things are the same. The mask and this the pipe is for the same. If you want to change any of these, you need to just change the machine, and then you can just plug in. Okay. So this for the BiPAP we recently submitted. It's not published yet. We are recently submitted, and this time actually we rotate for the visualization to show you. We just rotate this on that side, because if it is this side you cannot see anything. So that's why it's rotated that way. So we just showed here, and then we put a mask like that. Okay, and then this is now the inlet. So we are actually giving the positive pressure through this one, and then through the nose is inhaling. Okay. So you can see here the breathing volume flow rate at the time. So that is our the input we just got, and now these are the parameters actually we applied. We applied three pressure. Okay, it's called the IPAP and EPAP. What is IPAP? IPAP is the inhalation positive airway pressure, and EPAP means exhalation positive airway pressure. Okay, so the maximum IPAP by minimum like a maximum EPAP. So this is the way normally in the machine it is written there, that what is the maximum 12 by 8, 16 by 6, 18 by 8. Okay, so 12 means the maximum IPAP, 8 means the maximum EPAP. So this is the configuration. So we just applied, and this is without BiPAP. Without BiPAP we did not apply anything, so 0. Okay, then we applied these three configuration, and we just observe. These are the observation. So without BiPAP, and then use IPAP by EPAP is 12 by 8 centimeter H2O. Okay, and then 16 by 6, and then 18 by 8. Okay, so these three cases we I studied, but as I said, I don't know which one you need, so you have to go to the doctor, they can set it up. Okay, the 18 by 8 for you, or 16 by 9 for you, or something, they will set up in the machine, and then you can. We just study these three, people normally use these three kind of scenarios. Now the heat transfer. Okay, we study some heat transfer into the lung. You know why you study heat transfer? Because when I was very small kid, my dad used to tell me when I go out during the winter to use the muffler. You know muffler we use? The guy is using it. Yeah. We use here to close this one. That time I didn't know why do we need it. Maybe to make us warm. So that's it. But when I did this research, I found it is very important. If you do it, is very, very important. Because you know our body temperature is 37 degrees, right? It's 37 degrees Celsius. And if we inhale like a 0 degree or 4 degrees temperature of air, so it will go through your conducting airways. And if the outside temperature is very cold, okay, like about the same temperature as you are inhaling, only the small part here. So that means there is not much heat transfer happening. So that means you are actually your cold air is going very deep airways. So if the cold air goes very deep airways, then it's very, very bad. You will catch cold. Okay, some bronchitis can happen. So that's the reason we just use this kind of things. We just protect our this one. If we can protect this one, it can give you your body release the temperature, and your because your the muffler material is insulated. So that means the heat will be here. So when you are inhaling, the heat transfer happened. So that means your 4 degrees or 0 degrees temperature air can become 35 to 37 degrees when it comes to the end of the trachea, and you are okay, nothing is happening. So it is. So from that inspiration, I just did some study on large density simulation of heat and mass transfer in a human respiratory system. Okay. So we published so much 2 papers, and this paper is the very extreme cases. The first one we did some 5 degrees, 20 degrees and 44 or 45 degrees. Okay. And this study we just made the lower, minus 20 degree and minus 5 degrees. Okay. And you can just observe the cold air you are inhaling from here. Okay. Your cold air inhaling, by the end of the trachea is almost getting the body temperature. Okay, is becoming because we on the surface we applied 37 degrees. Okay, but if it is not insulated, it is not be always like 37. It will be lower at the if you go to the outside during the winter. Okay, so these are something in the nose. Okay, this some cross section is just D and E, and they are like here, the cross section here. And also we just realized that, as I told, the larynx area here we can see a lot of vortices happening. That's why I just applied the large density simulation to observe this turbulent effect. The turbulent is here, but it takes long time for the simulation. So one simulation it take about 2-3 months, because large simulation it takes a lot of time and it needs a lot of mesh. Okay, and so it's very hard to compensate. So this way you can see how these vortices happen. The turbulent actually happened for this lower Reynolds number. I have to check. I think we use about 7 million mesh for here. But we have to run it for longer time because it's a time dependent. It's not a steady state. Okay, it's a transient. Alias, alias. Yeah, but you have any node problem, like you have sufficient number of node you can use? How many node you use?
No, sir, I'm asking the number of meshes compared to k omega, like Alias use more.
Alias takes more mesh, and I think it's not 7 million, I think more than that, because 7 million is for the k omega. I think this one I done information not here, but in the paper we have. I can't remember here, but yeah, it needs more meshes, especially near the boundary, because they just treat the alias, so they treat the boundary very well. So we need to keep more mesh near the boundary. So now we see the detailed temperature analysis from this study reveals that how inhaling cold air at minus 5 degrees Celsius and minus 20 degrees Celsius affects the human respiratory tract, highlighting the system's efforts to warm the air as it moves from the nasal cavity to the primary bronchi. Okay. So the respiratory system's ability to warm inhaled air is challenged at extremely low temperature with cooler region, okay, especially at minus 20 degrees Celsius, leading to a incomplete warming by the time the air reaches deeper regions like the primary bronchi, and that can actually affect. Okay. So the presence of cooler temperature in the lower respiratory tract can cause thermal discomfort, increase the respiratory resistance, or damage the delicate tissues, particularly with prolonged or repeated exposure to extreme cold. All right. Now the another case, I am just showing all the cases, possible areas. So this paper is finished just now. We did not finalize the paper yet for the publication. So here we just use some helium oxygen mixture for drug delivery. Okay. So helium and oxygen mixture. So we just found that for only oxygen we are inhaling, that can cause some turbulent effect in the larynx area. So that means when we are inhaling the drug, it actually deposit on the upper airways, but you need to send it to the deeper airways, the medicine, but it's stuck somewhere here. So that means you need to make it laminar. How can you do that? So if you use helium, so your turbulent flow for air become the laminar flow. So that means in that mixture we are using about 80% helium and 20% oxygen. So it's called Helox. Okay. So this Helox mixture can actually help. You see how this they make mixture, 79% helium and 21% oxygen. So this is acceptable range, but for long time it is not good. Okay, because if you inhale a lot of helium, is not good for your health. But for drug delivery, for a small time is okay, is approved. But you cannot inhale helium for a long time. So this is the another way of you see the turbulent on the left side. Left side is the turbulent, and then it becomes laminar because of this the properties of this Helox. So the property actually change a lot. So you can see this study on you can see on the left one is the only air and the right one is the Helox. Okay, and we use 1 to 10 micrometer, 91 to 100 micrometer. So it's a huge range, and we actually clustered. Okay, so clustered 1 to 10 in one cluster, 11 to 20 another cluster. So this is the way we just presented here. But the range is from 1 micron to 100 micrometer size particles, and these are the cluster, and you can see for only air how it is affecting, and for Helox how it is affecting. You cannot see it properly from here, but if we can go to some pressure and the velocity analysis, you can see there. So here you can see on the left side is the air. Okay, you can see some the particle are actually depositing here. Here is just larger particle also going to the deeper airways. Okay, but they are actually larger particle actually deposit on here in the back of this there, so you cannot see it. So it is depositing here somewhere. But when you use Helox, it is going to the deeper airways, and if more you can see here, you can see the control for the turbulent kinetic energy when inhaling air, and B is A is air, B is Helox. So you can see here high value, okay, the kinetic energy, but here you see the low value. At the same time, the turbulent kinetic energy for exhalation, this is for inhalation. For exhalation, we have for only air, we have some higher value. We just observe higher value for Helox at 1 second. For exhalation is for lower value and is very smooth. Okay, you can see in that critical region is very smooth, but here we have higher value. So this is one way for the drug delivery. It is not very popular, but they can actually use it. What else? There are some other things. We did some other study. It's called the targeted drug delivery. So you know that in every medicine there are some side effect. Okay, even the paracetamol. So if you eat any medicine, it has some side effect. You cannot just use it for maybe you are feeling pain here. It will only work here. It will work all over the body. So, that means in some places you do not need it, but you are taking it. So, it is actually is not very good. So, that is why recently targeted drug delivery is becoming very popular. It can only affect in that place, okay? Especially for cancer chemotherapy. So, when they call it like a targeted drug delivery, but it is not actually targeted drug delivery. They give some specific criteria. The cell which grows faster, they will affect that, right? That is the way they give the chemotherapy. But it actually attack your hair, okay, because hair grow faster. So, at first it affect your hair instead of the cancer cell. So, that is why just trying to get some targeted drug delivery. So, we just we did not do much work, but here we just only did for we just created some magnetic field. For example, we have some issue on the left lung here. So, we just created some magnetic field here, then we are inhaling the magnetic particles, drug particles, and they are actually going only here. It will not go to the right airways. So, that means it is actually helping you. It is not going and affecting some other places that you do not need it. Now, I just finished my CFD part. Now, we want to talk about some molecular dynamics simulation. So, I will not talk much about the structure and the methodology, but some physics. So, what we did here is that gold nanoparticles we use for drug delivery, we use for two cases. So, our study actually we can identify both positive and the negative. Positive means we can apply this technique for drug delivery, and negative means we can analyze for like pollutant particles. Okay. So, two ways we can actually analyze our results. Gold nanoparticles also can be treated that way, like the people who work in the gold mining or like the goldsmith who makes the ornament. Okay. Whole day they work with that and they also inhale some gold nanoparticles. So, we need to see how it actually interact with the lung surfactant. So, what we did here is we just did two things. One is the naked gold nanoparticles, okay, just gold nanoparticles, and another one is gold nanoparticles coated with lipid, okay, coated with the medicine. Okay, these two way we just release the particles and then we just observe how it is interacting with the lung surfactant. Okay. So, before that I just want to tell a very quickly about the composition in the lung surfactant. So, as I told you before, it start from the 18th generation, and that is the alveolar sacs, okay. And inside the alveoli, so we do not have any mucus here. You remember, there is no mucus in the alveoli. So, what we have a thin layer, okay. We have a thin layer, is called the lipid monolayer. So, lipid monolayer is having is here, then we are inhaling the oxygen, and oxygen is transporting through this because they are very porous. Okay. So, due to different density issue or pressure issue, so they just exchange, okay, from the capillary, the blood capillary outside this lung. You see all the blood capillary here. Okay. You can see the blue. Blue means they just come here, okay, and they are releasing the carbon dioxide taken by the alveoli, and then they are taking the oxygen back from the alveoli, and then they are becoming red and they go back to the lung, to the heart, and heart is pumping the pure blood to your body. Okay. So, now this surfactant has a very big impact, especially when the baby is born, when the baby grow up in mom's tummy. What happened is the last part of their body grows this one, the lung surfactant. Lung surfactant start to grow after 27 weeks, okay, after 27 weeks. So, that means if any baby is born, premature born is 27 weeks, it's very hard to make them live. I don't know in India, but in Australia, yes, I found couple of babies, they survived, but they need extensive care, because you have to put the baby somewhere artificially, so their surfactant grow and they can use their lung for the breathing. But up to 27 weeks, they cannot breathe by themselves. Okay, so and then when the baby is born, what happened? Did you see anybody? I don't know. But because I had the privilege in Australia, we can stay in the surgery room. Okay, when they do the surgery. So I saw my daughter when she was born. When the baby comes out, okay, they take the leg like this way, hold like the opposite way. Okay, they shake couple of times. Okay, and then they give some pipe to clear the nose and then the mouth. Okay, they clear it because lot of mucus there. So clear up, and then the baby cry. When the baby cry, that is the perfect moment. That is the enjoyable moment, because the baby can breathe. So that is the only time the cry is better. Okay, the other times we cry means we have sorrow and we are crying, but that cry is very important moment. So that means when the baby is born, their lung surfactant actually lapse. They are actually like this. Okay, because they don't need it. They breathe from the mom. They don't need it. But when they come out to the earth, the world, they have to breathe themselves. So that's how when they just cry, that means their lungs suddenly, this one actually make bigger, so they get the oxygen. And then from that moment, they start breathing. So this surfactant, so just that time it goes up, and after that it never collapses. Why they don't never collapse after that? Because there are some physics involved. It is called the surface tension. The surface tension make a major role here to keep the airway open all the time. Okay, so there are two types of surface tension for exhalation and inhalation, because when they inhale then it becomes big, when exhale it becomes small. So small means exhalation, the minimum one is 0 and maximum is 23. So these two parameters. So we actually for our simulation we use the two extreme cases. But now my PhD student is working on, there are some intermediate one as well. But in this case we use only two cases, 0 surface tension and 23 surface tension. Okay, and now underneath this monolayer, inside the monolayer is made up of like here you can see proteins, the lipid, 92% actually lipid and 8% protein. And the lipid has different types of lipid. Okay, so it has POPG, so there are a lot of different types of lipid here. They have like a cholesterol about 8%. Okay, POPG they have 9%. So different other composition. But since the DPPC is 41%. Okay, so because it is very hard to do the molecular dynamic simulation, because every like these molecules you need to tackle. Okay, so it computationally is it also very expensive. So one simulation I remember it take about 6 months. Okay, so that's why it is very difficult to consider lot of variables. Okay, so we have to limit the variables. So what we did is we just use DPPC and some POPG and also vary some proteins. Okay, 1 or 2 proteins we varied. And you can see there are some diseases. I'm not talking about the COVID-19. So COVID-19, I think they also had this kind of thing. So that is the most dangerous things. We know that we see sometimes some old people, they just tell that the water stored on the lung, something like that, right? So that water and this water is different. That water, they go to the hospital and they take the water out from there. So that water is between the lung surface and the parenchyma. So in between there are some water actually deposit. So they are actually is attached such a way there is no mechanism, like there is no like anatomical things to attach, but the surface tension. For example, if you take two glasses and you put a little bit of water and attach together, can you take it off like this way? You cannot. You have to take this slide. Otherwise, its surface tension is so strong. So that's the way our lung is attached with the parenchyma, that way. So sometimes water actually penetrate here. So that's why they deposit some water and it makes a lot of problem, breathing problem. So sometimes they need to go to the hospital to take the water, like 1 liter, 2 liter water, they take it out. But this water is different. This water means this actually closing your airway sucks. So it is very hard to take this water out. You need some medicine to dry this water. Otherwise, there is no oxygen and carbon dioxide exchange if it is full of water or something. Okay, so it is a very severe problem. And you can see how this oxygen and the carbon dioxide exchange happen. Now this is the configuration. I am not going in very in depth here. So in the modeling, what we do is we just take a rectangular box. Okay, so it is vacuum. It is also vacuum. So in CFD normally we just do one side, but in molecular dynamics they have to do like a periodic things, both sides. Okay, so these are your the lipid. Okay, lipid head group. So this is the lipid head and this is the lipid tail and this is your water. So the water and the lipid, they have some like hydrophobic and hydrophilic condition. So they are actually hydrophilic. So that means the head actually attached to the water, and if it is and the tail is hydrophobic. So that means it goes out of the water. So this is the water. This is the way they interact. Okay, and I just give some information here how to use with some Martini coarse graining. Force field is all about Newton's second law of motion. So it is nothing but that one. Okay, and we observe here for single particles, 4 particles, 8 particles, 16 particles and 36 particles, and you observe how it is interacting with the lung surfactant. So you see 9 particles, 16 particles and 36 particles. So this is one view from the top view and this is from the side view. And we found that for highest number of particles, some pore actually form. So pore form means something will go inside. So it is dangerous. Okay. So pore formation means your lung surfactant is damaged. Okay. So that's why the water can go inside or something. So this is the way it can happen. So that's why the concentration of the particle, the amount of particle we are inhaling is very important. If we inhale lot of this kind of particles, that can damage our lung surfactant. Okay. So now see the single particles, how these nano particles actually interact with the lung surfactant. Okay. So it is not penetrating into the water. So it is in there. Okay. It is not going. Now the 9 particles, they are actually interacting there, and then 16 particles interacting, and then that is the 36. Again you can see the pore formation happen. Okay. So the last one is the mucociliary clearance. Okay. So, the mucociliary clearance, as I told you before, that we have some cilia underneath the mucus who is using like working like as the brush, okay, brushing your mucus. So, in our study what we have done is we are still working on this area, but initial work was to make the cilia and make the movement. But how to do that? Because it is 3-dimensional effect. It is not like going this way, coming this way. Then it is very easy. It is like going this way and then coming back this way, and going this way, coming back this way. And not only that, it is actually going this and that way as well. So both way. So that's why it's a very, very difficult. Then from Singapore National University, we just collected this data from them. So they have like a 12 profile of the cilia movement. They have 12 profile. Okay. So we get all these mathematical equation for this profile, and we applied these things in our model, and then we run it, and then we just see that the profile is moving. Okay. So this is the real cilia. You can see the top it from the experimental from the experiment. We just got this one. So now it is there is no sound for this. So you just see here how you are inhaling those particles, and those particles on the mucus is on the mucus, and mucus is taken up. So you are actually, when it comes here, you are actually eating it. Okay, it's just moving with the mucus, and underneath the mucus the cilia is here. Okay, just see the single cilia, and it is not a 2-dimensional. It is actually as a 3-dimensional effect. It is going in every direction. Okay. So this is the single cilium. We call them cilium, the single. Okay. This is their movement, and then we just multiply with this. So this is the way this is the experimental data. Okay. So this is the way they have the movement. They are taking the mucus from there, but this is not the real velocity. The real is very fast. Okay, it is slow just for that. Now we covered with the water, and on top of that the mucus layer is there. So now it is actually taking your mucus from your conducting airways. Yeah, and the particles on top of that. So that see the particle is not penetrating. So it is safe. If it goes underneath, then problem. So it is now taking away. So it is very, very slow, just for the demonstration, so that you understand how it is moving. Now is increasing from there to the maximum 10 millimeter per minute. So that is the maximum. That is the way is always clearing up our lung. Okay, very, very fast. We have some experimental data as well. Yeah, this is the real one. This is what actual things happening in our lung. How the mucus is taking you see all the particles you are inhaling, they are taking away. So this is the modeling we use for 3 different cases. One is 3D cilia bead motion. 3D means all sides it works. One is 2D cilia bead motion, it's called a planar, and one has some steep planar. It is not bending, it's just going there and there. Okay, maybe if somebody has some disease, they have this. So it is my long-term plan. That's why I am collaborating here in IIT Kharagpur, that whether we can create some this artificial cilia or not. Okay, if we can make this artificial cilia, it will be very, very helpful to treat the asthma patient and also the COPD patient who has some cilia dysfunction. So I don't think that it will be very tough, because we already know the profile and it is actually working. Then we can use some biocompatible synthetic or something, and we can put some like a battery, okay, and then we can just put where you have some problem. Because if you don't have cilia somewhere, that means your mucus is not clearing out. So your mucus is stuck there. Okay, so that means it's slowly gathering your mucus and it block the airways. Okay, but if you can somehow put this one in there, that can actually help you clearing up. Okay, so that is my ultimate goal of doing research in that area. You can see the animation, if you can see from the back. The 3D effect you can see from the side view and the top view. Yeah. That's it. Thank you very much. If you have any question.